Hi, I'm Austin Magsig. I'm a senior mechanical engineering concentrating in aerospace, and my project is working on a nozzle modification design for the Boston University Rocket Propulsion Group. So for those that aren't familiar, the Boston University Rocket Propulsion Group is aiming to become the first collegiate rocket team to send a rocket to space. And by space, we define that as the Kármán line, which is 100 kilometers of altitude above the Earth. And so just what the current mission is, we have the Lotus Dev 2 engine on board the Starscraper rocket, and the yearly budget for the team is about $100,000. So that's something to keep in mind as as the presentation goes forward. Just to give you an idea of what the trajectory is for this rocket, it's more like the picture on the left, or the trajectory on the left, where it's a single-stage rocket, flies up to about 100 kilometers, and then falls back down to the Earth. Whereas on the right is more of what you would see with SpaceX flight, where it's a multi-stage rocket. You send the first stage sends the rocket into space, and then a second stage sends a payload into some sort of orbit or other trajectory. And so a little bit of the background, the theory behind all of this, we can get a pretty good estimate of the maximum altitude reached by a rocket based on the first equation at the top. And that's a function of specific impulse and mass flow. And so specific impulse is basically the efficiency of the rocket, how much thrust you get out based on how much you're throwing out the back of the rocket. And we can compute the rocket thrust based on the third equation there, which has two terms mainly. It's the effective exhaust velocity of the gases multiplied by the mass flow. And then there's a second term where we have a pressure difference at the exit of the nozzle, and you multiply that by the area to get a force. But ideally, when you're designing for rockets, you want that second term to be zero. You want to design for that to be zero because it's much more effective to convert, basically using the last equation, converting pressure to a gas speed, and you get a much better thrust much better thrust from doing so. So just some of the stats on the engine itself. It's a liquid rocket engine using isopropyl alcohol and nitrous oxide, about 230 seconds of specific impulse, and we use a flight sim code to calculate kind of a baseline altitude for the current rocket, and we reached about 100 kilometers with no payload on board the rocket. Obviously, the code makes a lot of assumptions with the calculations, and it's assuming the rocket is operating ideally, all functions are working. So it's just something to keep in mind. It's a general estimate of what we can do just using the specs from the engine itself. So just to give you a picture of what this looks like, what the engine looks like, on the left you have the full assembly here, and on the right you have just the chamber itself. And two of the main features to keep in mind is if you look in the bottom right, there's a channel on the wall of the nozzle where the fuel flow runs counter to the exhaust gas that's coming out of the bottom, and then as it comes up and is injected from the chamber at the top. And what that does is the fuel is a lot colder than the gas is coming out, so it keeps the walls of the nozzle a lot colder than if you didn't do that. And the second feature is the retention ring at the bottom that holds everything together. That'll be important for the geometry of our design later on. So when you look at all this, there's a couple different ways you can improve the performance of a rocket engine. You can alter like the fuel ratio, the fuel type, kind of the chemistry behind it all, or you can optimize the geometry of the chamber, the nozzle itself. And so that's, if you couldn't guess, that's what we're doing. Altering the systems and the fuel and all that is a really big undertaking, and it's basically what the team is working on itself. But as a team of two, me and my teammate Edward Zuniga, who's not in the Honors College, but we're working to optimize the nozzle and create an extension on the back in order to improve the thrust and the performance of the rocket engine itself, which is a lot easier to do given a semester in a team of two. And so basically we create this design, we have to write a detailed report and present our findings to the group and give them a reason why they should consider implementing this into their current architecture. And so the goals of the project are to increase the maximum altitude that it reaches, make sure that it's able to easily integrate into the current rocket. Basically, our goal was to just slap it on the back and hope that it increases the performance, gives it a lot more thrust. There's some engineer constraints with thermal management and the structural integrity based on the high high temperatures of the gas coming out the back. And it has to be cost effective. Like I said, the budget's about $100,000 per year, give or take, based year to year. But so we don't have unlimited funds where we can just use the most, like, any kind of like economical sense to the for the materials that we're using. And so we iterated through a bunch of different design variables. And so looking at the material and cooling method, we wanted to keep the radiative. That was a big, the thermal management was a big design driver because the gas out the back is really hot. And using regenerative cooling, which is what the current rocket nozzle does, would be really hard because you have to reroute that through the back of the nozzle extension. So being able to use radiative was really important for us. And in order to do that, we had to come up with we had to find composite materials that would satisfy the thermal constraints. And so doing so, we're using carbon fiber because it's a lot better than a lot of the metals were basically melting using the wall temperatures that we were looking at. The nozzle itself is going to be stationary. Using an adjustable would have added too much weight and wouldn't have been really effective enough to be worth it. And our goal was to bolt it on using where that retention ring is. It's already bolted on. Basically, we want to replace the retention ring and then bolt the nozzle extension on that way. And then we want to optimize the exit diameter and the angle of the nozzle in order to improve and optimize performance. In doing so, we came up with this preliminary design of experiments, which gives us, we use 2 degrees of freedom, the launch altitude and the exit diameter. And so if you look at this plot on the left, each line is a plot based on different launch altitudes. So starting at sea level at the bottom, and then as you get higher, it's about 30 kilometers at the top. And so, and then each curve themselves shows how the maximum altitude that the rocket can reach is a function of the exit diameter of the nozzle out the back. And so using the current launch altitude, which is about 1.2 kilometers, we saw that the peak altitude that we could reach was about 6.5 to 7 inches. So somewhere in that range is where we were kind of aiming for. So looking at, we used computational fluid dynamics solver in SolidWorks based on the CAD models that we had. And this is just a picture of what the pressure looks like in the previous nozzle. So you start with really high pressures in the back in the pressure chamber, and then it's pushed through the throat, and then expands out the back to the exit where the exhaust is, and so you get really low pressures out the back. But then as we added our nozzle modification onto the back with a exit diameter of 6.7 inches, and we used the same angle that the previous one, the exit angle that it had, so that way it was a smooth transition. And then what we got when we ran the simulation is we saw a much lower pressure out the back than before, which is good for higher flight when you're higher in altitude, because as you get higher in altitude above the Earth, the pressure in the atmosphere gets a lot lower. And so, most importantly, looking at the Mach number of the gases, and so the Mach number is just the speed of the gases divided by the speed of sound at that temperature. And so you start from really low speeds in the chamber. It's accelerated to 1 through the throat, and then out the back, as the pressure expands, or as the gas expands, pressure decreases, and the Mach number increases. And so we're seeing a Mach number of about 3.4 towards the center of the nozzle, and then as you get further out towards the walls, it's not as fast. But then with our new design, you allow the gases to expand more, and that's really important because it allows the speeds to increase. And so when we ran the simulation with our new nozzle modification, we saw a Mach number of about 4 near the center, and then a little bit less towards the walls, but it's better than what it was before. So that helps increase the thrust of the nozzle itself. So just looking at some of the constraints, this is just a steady-state thermal analysis of the walls themselves. The line at the top is the melting temperature of our carbon fiber that we used. And then you see that the temperatures of the walls are rather high. They're 1600 Celsius, but still significantly lower than the melting temperature of the material. And looking at the structural analysis, we saw that the main stresses in the walls were due to the thermal stress, which is caused by the gradient of temperature from the inside to the outside. And it's still much lower than the yield stress at the top, where you'd see failure in the walls. And so just the CAD drawings of our nozzle itself. On the left, we have the nozzle by itself, and you can see the bolted pattern is based on the retention ring bolt pattern. So you just slap it on the back, and then as it's all assembled, you have the picture there on the bottom. And so after running through all this investigation, we found about a 4 to 5 kilometer increase in altitude, in the max altitude. So about a 5% increase on the baseline altitude from the original nozzle, and integrates really easily with the current architecture. And so we found that with reasonable manufacturing costs, so if you say it's a 5% increase in performance, take about 5% of the budget, so a couple, like $4,000 or $5,000, which we expect you could manufacture for that much. This would be a worthwhile endeavor for the team to implement on their rocket. So that's it. So thank you. That's a lot. So if anybody has any questions, feel free. Yeah.
You mentioned that your team, the BURPG, is hoping to be the first college-age team to get a rocket into space.
Yeah.
Are there any other teams in that?
Yeah. There's about 15 or 20 competing to become at different schools throughout the country, and I guess the world as well, competing to be the first to reach 100 kilometers in terms of like competitive teams. And then the current record is 44 kilometers. That was reached by University of Southern California last summer, I believe. So that's another thing to keep in mind, is even though like 4 to 5 kilometers doesn't seem like a lot, at this stage any improvements help. So